We are all welcome to today's session of the AI Essentials Workshop series. And I hope you are all ready to partake in this and make good opportunity of this workshop series. My name is Sana Dalasi Anyamu, and I'll be your moderator for today. So, first off, we would like to look at an overview of all that we.
Hi everyone.
Hi, Kekeli.
Hi Senal. Thank you for the opportunity giving me.
Okay.
Um, um,
So, I'm currently giving the overview for the AI training, and I'm
okay.
on week two. Okay. So for week two, we'll be looking at prompt engineering. Hekeli, the floor is yours.
Okay. Okay. Thank you so much. Thank you so much, Sena, for welcoming me. So good morning, afternoon, and evening to everyone around. My name is Kekeli, and I'll be introducing us today to the world of AI, artificial intelligence. So we know how AI is rapidly developing and how it is changing things we do and how it works. And as engineering students, we know how AI is changing the whole field of engineering. And so we need to know how AI basically works and you know also how to use AI. So please let's proceed. Okay. So please can you go to the next slide? Good. So today's workshop will basically explore some essential concepts of AI, yeah, particularly for engineering students. And then we'll also gain insights into various AI types, their subfields, and some practical applications in engineering. Please proceed. The next slide, please. All right, good. So we would like to begin with the definition of AI. So when we hear AI, what comes to mind is artificial intelligence. That's basically the meaning of AI. So it refers to the simulation of human intelligence processes, sorry, by machines and in particular computer system. So just as we've watched certain movies where they use simulations to gaming simulations or virtual simulations. We are saying AI is just one like that. It just mimics the human intelligence. Mimics how the human or the human brain acts. So, and these are some characteristics are like speech recognition, learning, planning, and these are some things that um we find AI doing, okay, acting out like humans. So some examples are like ChatGPT, self-driving cars, Face ID, and over here I think we have the first picture over there, um, which is a self-driving car. As you can see, we can see something being mounted on top of that car, right? And that is what gives that car the vision to be able to drive around in town. In our next image, we can see some robotic automation in some industry over there. So we've seen certain movies or videos or pictures of robots trying to build cars or even segregating necessary items in the just the basic um, task of an engineer is to solve problem. That is the basic work of an engineer. So one in solving problems, we will not want to complicate certain things for ourselves. So we like to make work easier for ourselves. And so one main thing is to automate repetitive tasks like report writing and testing. Imagine writing performing some experiments. All right, so you're doing some experiments, and then with every small thing you have to write this down. With every small thing you have to write this down. With every small thing you have to write this down. But then with AI, you are given the chance to with AI, you are given the chance, sorry, you're given the chance to actually write all that you need to do within a fast time and a short time. You don't do it manually, maybe with a pen or type it out. You have your AI there, which is going to help you out with all this. And also, it enhances problem solving. So through data driven insights. So um, there are some, there could be some problem, let's say at SES, for example, and you collect some amount of data, right? And you need to, make a progress. So you are like, how many chairs are needed maybe for SES? How many chairs are needed for this? By gathering your data and feeding this into an AI system, this can actually help you in deciding or coming up with a solution to what problem you want to bring on board. So that's another benefit. It also speeds up design and simulation processes. So imagine working, let's say, in a company, an industrial company, where you have to design a machine, right? Right now, through prompt engineering and through generative AI, you can just prompt your maybe and your AI bot or whatever. You give it this particular features or parameters to follow, and will be able to design everything for you without you now going to sit down and say, let me open SolidWorks and let me start drawing from scratch before you send to the CEO and then they reject it and then you come back. So there's another thing. It also improves system monitoring and failure prediction. So let's see, there's another example where you have computer vision being applied over here, and it scans your work. Let's say in an industry, it looks at maybe the efficiency of a particular part of a machine, and tells you, when we use this for this particular time, this was going to happen to this part of the machine, whether it's going to last long or it's going to fail or what's going to happen. Good. And so these are some of the reasons or benefits of AI for engineers. So move to the next one. So we'll, there are three categories of AI. We have the narrow AI, the general AI, and the super AI. So the narrow AI is designed to perform a specific task. So it's limited to doing one task. It doesn't do multiple tasks. So you have Siri, you have your facial recognition, you have a facial recognition app or software on your phone. You have spam filters in your email. You have ChatGPT. You have a whole lot of them you can mention. And you have the general AI. Oh, sorry. You have the general AI, and this is an AI that can learn, perform and perform any intellectual task a human can do. So, like a robot that can solve math, cook, and write poems like a human. You have the super AI, which is an AI that surpasses human intelligence in all aspects, like creativity, decision making, emotions. Right. So, in our current world, we are limited to the narrow AI. We've not crossed that boundary into the general AI yet, because all models we see, all AI models and stuff we see around us are basically data fed. They can't reason on their own. Yes, unless you give them an input which is a data to perform, they can't do anything on their own. Yes, so they can't do certain tasks on their own. Yes. So some real world applications, we have the virtual assistants like Siri and Google Assistants, Alexa, and co. We also have advanced technologies in healthcare, such as diagnostic algorithms and personalized medicine. So those in biomed can testify to such things and such things in healthcare, like the diagnostic algorithms, where you can have a model which is able to predict if a person has cancer or not based on the images acquired, maybe X-ray images or MRI images. And then also in industries, they utilize AI for data analysis, customer service automation, and predictive maintenance. So consider an industry like MTN. MTN uses your data feedback. So whatever customers see about this network, oh, this network is bad, this network is this, they gather all this data, right? And then through data analysis, they're able to tell which problem is persistent, which problem is this, which problem is that, and then they're able to act out very fast. Also, there are also chatbots for customer service. You can go to different websites and you find chatbots where you can question them, ask them to help you out in solving maybe an issue. For example, you go to the Telecel has some bots where you go to their app, right, or their websites. They have a bot over there where if you have an issue with maybe your mobile money or airtime or something else, you can ask them. You can ask that bot, sorry, and then that bot is able to give you an answer to help you out. Also, um, you have image-based search. Example, Google Lens. So you have Google Lens where you just pick your phone and snap, and then it's able to um, pick out that image that you took, and then maybe search things based on that image. If it's a cat, it picks the image of a cat, and then it's able to search like images of cats for you or whatever you want to do with that. You also have robotics and smart automation. You have drug discovery. So let's see some of the core subfields in AI. So one is machine learning. So machine learning is a subset of AI that focuses on the development of algorithms that allow computers to learn from and make predictions based on data. So machine learning, that's just fun. So it's a machine that's just trying to learn. Just think of that. And how do humans learn? So every time we go to our rooms, we go for our slides and we read, right? As we read, we train our minds with whatever things we find in the slides, right? And so when we are asked questions, we um, answer based on what we understand and what we've learned. That's just basically how um, machine learning is. So you develop algorithms, okay, and these algorithms are mathematical functions, okay. You develop algorithms, and then these algorithms are fed in with data, and then they predict or give you an output based on what's what the algorithm is and also what the input is. So it encompasses several techniques. These are the major ones. You have the supervised learning, you have unsupervised learning, and reinforcement learning. So we'll get to see about that in the coming slides. So some algorithms over here are linear regression, which I think most of us know of. Like there's a simple equation of a straight line y equals mx plus c. That's a particular one. You have decision tree. So just picture the decision tree as a major tree with branches and then sub branches. Okay, it's also used in decision. So if, let's say, you want to go and play outside, so you branch your question: will it rain? Yes or no. Will it? If it's not rain, then will you do this? Will you do that? So all these things will actually come out to a final decision where you would be um able to let's say judge what you want to do. Okay, so you have the support vector machine, and you also have the k-means clustering. The k-means clustering is basically for grouping things together. Okay, so let's proceed to the next thing, which is neural networks. So neural networks are computational models inspired by the human brain structure. So they consist of interconnected nodes organized in layers, an input layer, or an input layer, one or more hidden layers, and an output layer. So over here, we can see the pink ones to be the input layer, the orange ones here to be the um, hidden layer, and then the blue one here to be the output layer. Now, whatever you feed in here has whatever you feed in here is what the hidden layer will actually look at. Okay, so there are weights assigned to this pink stuffs here, and then the hidden layer is what is actually going to process it. It's going to learn like what is from this input layer. So the data comes into the input layer, and then the hidden layer sits and analyzes and processes what's going to come in there and learn certain things before making a decision. Okay, so a neural network can capture nonlinear relationships in data, right? And then making them powerful for tasks such as classification and regression. So an example is a email spam detection. So to, let's say, you are not used to receiving certain emails, okay, and you want to know if maybe it's a fraud email, or um, it's just not a regular email that you receive in your mail. What happens is, if you have, let's say, a neural network model, okay, which is going to move this email to your spam for you, what it will do is that it opens the mail, right? Sees what features are in that mail, which doesn't qualify it to be like to find itself in your inbox or to be an important mail. And what it does is it picks certain features. So it can look at maybe how the words are written, like how organized these words are. It can also look at the type of mail being sent. So let's say a UG mail like this. Many a times we would expect to receive mails from, let's say, at ug.edu.gh. But as the case, you are receiving mails from unverified random places. So what happens is this system has some spam detection models, okay, which are able to segregate this mails and then classify them as spam. So it sees certain features. Oh, okay, this mail is not verified. This is not usual, and so let me send it to the spam side. So sometimes we you might even send a message to a big company or something, and you'll not find it in their inbox. You might find it in their spam box, and this is just one of the things that happened. Then we move on to deep learning. Okay, so now deep learning is more as a combination of more neural networks actually. So it's a specialized field within machine learning that utilizes neural networks with many layers. Okay, so it has in the blue side we have the inputs, but if you look at the green side, this are where the layers are. The hidden layers are. There are numerous over there. You can have some with over 1,000 hidden layers over there. Now, what makes the deep learning ahead of the normal neural network is that it has these numerous hidden layers which are able to learn particulate features. Okay, so just like for instance, if you have, let's say, use a neural network for facial recognition, just a normal neural network for facial recognition, what happens is, let's say, it just picks, let's say, four features. So it just looks at the color of your face, looks at the size of your nose, maybe the size of your eye and the size of your mouth, right? It just picks that, and then that's all. Imagine having something like that. What happens is, um, if you don't take someone with the same features might actually open your phone, looking at just the size, the color, and everything. But with deep neural network, it actually goes deep down into like picking different features. Some could look at the actual shape of your eye, the size of your eye, the size of your pupil, and a whole lot of minute features that you might not assume. And that is why it's mostly used also for facial recognition. So we have CNN, which is a convolutional neural networks, sorry, which is used for image task. So you have like ResNets, EfficientNet, UNet. So these are powerful CNN models which are used for imaging, and mostly people use them in medical imaging. You have recurrent neural networks. You have the LSTMs, the long short term memories. You have transformers for sequential data. So the transformers are you find transformers in this is a model architecture for models like ChatGPT. Okay, and then you have the GAN, which is a generative adversarial network. So these ones are capable of generating contents like text, image, and sound. So some applications of this deep learning is facial recognition, as I said earlier. You have self-driving cars. You have AI generated art and text from models like DAL-E and then ChatGPT. Now, move to the next one, which is large language models. So, when you hear large language model, what comes to mind is um, having a whole vocab or a whole container of multiple texts. Okay, having the whole vocab or container of multiple texts being fed into the model. So these AI models are trained on like huge um, amounts of text actually, and then they learn this grammar, facts, logic, and reasoning patterns. So they pick, let's say, textbooks, papers, or whatever, and then they submit it to this model. Okay, and it picks this word by word, word by word. Okay, and breaks the whole thing down into words, and then picks them and then trains itself. Okay, now in doing that, it just doesn't pick maybe a word and say um this word means this, and so in this context it might not mean this, it might not mean that. But then it uses certain patterns, okay, some reasoning patterns to identify and know that okay, when this word appears here, it means this. When this word appears here, it means that. Okay, so it's built using the transformer architecture. So the transformer architecture, that's what's called a self-attention. Okay, the self-attention is basically focusing on one word, like or focusing on certain words in a sentence. Okay, and these words actually are what will make the model know the meaning of that statement. Okay, so it's, let's say it takes one particular sentence. Let's say it picks one sentence and then take certain particular words from that sentence and then run them parallelly. So maybe in this parallel side, in one side, it's using these words to mean something else this way. It's using these words to mean something else this way. Then at the end of it, there's one that comes out to be the best, right? It picks that whole sentence and then explains it to you. So that's what it does. It also generates or understand human-like text. So large language models, they generate or understand human-like text. They produce text, and they all work based on what we call NLP, the um, natural language processing. So now, what can LLMs do? They answer questions, they summarize documents, translate languages, generate reports or emails, write or review code. So basically, what we use ChatGPT for, when we are given assignments, we send the assignments to Chat to solve for us, to explain to us, and to um, actually explain certain things to us. That's just basically what most LLMs do. So example is ChatGPT from OpenAI. You have Claude, which is from Anthropic. You have Gemini, which is from Google, and you have LLAMA, which is from Meta AI. So now we have generative AI too. So there's generative AI. They create new content, okay, like text, images, audio, video, or code. Now they are also trained on large data sets, so it's text, images, and whatever. So you find that ChatGPT is also um, a subset over here. So it uses models like transformers, it uses GANs, um, it also uses VAEs, which are some auto encoders. Okay, it uses all these models in coming up with text and images or sounds, whatever. So they also learn patterns, structure, and style of data. So they go deep down into picking certain features from that, and then they're able to bring out or generate new ones that resemble what you have actually sent in. So sometimes you see there's this current trend on TikTok where people, you know, um send in prompts the AI, okay, prompt chats, and then they upload their picture and say ChatGPT should, produce a blurry effect or blah 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 blah. So what ChatGPT does is it's actually takes the text, but actually ChatGPT does not generate images. Okay, it doesn't generate images. ChatGPT is solely a large language model, so it doesn't generate images. It generates just text. But then how we see images over there is it communicates with other models, okay, like DAL-E. So it communicates with DAL-E, and then DAL-E is what actually brings you the image. So it communicates with DAL-E and then sends it back to chat. And chat shows you the image in your box over there for you to see that um, this is the prompt that you've given it to it. So that's what Gen AI is about. So you have ones that generate text like ChatGPT, Gemini, and Claude, and you have the images one like Mid Journey. You have DALL-E. You have videos. For videos, you have Runway ML. You have Sora. For music and sound, you have Suno AI. For code, you have um, Copilot over there. You have Codium. You have there's one called Lovable. There's one Bolt.eu. So these are generative AI systems. Okay, these are generative AI systems that actually create new things based on what has been sent into it. So now let's go deep down into how models are being trained for them to actually bring out such features. So what's an AI model? So we've been saying model, model, model. An AI model or a model is just a mathematical function that maps input to output. Okay, so it learns patterns from data by adjusting parameters. So we can consider the linear function y equals mx plus c. So from our linear algebra, we know if we have a value for x, a value for m, and a value for c, this is going to affect the output, which is y. So x now is our input value, which is termed feature. Okay, so we call that features. This we call the input data a feature. Then we call the output a prediction. So M and C are parameters or factors that would actually define the relationship between X and Y. Should we have a value of, let's say, C to be 0 and M to be 0, we'll have y being equal to 0. If we have a value of m to be 1 and c to be equal to 0, we have and then x also being equal to 1, we would have y being equal to 1. So this parameters tweak or determine how the output will be like. So consider the normal straight line. When we change the values of x, let's say x is 2 and y is 2. When we change the values of m and t and we plot it on a graph, we will definitely see how the lines change in maybe direction, or maybe we might have a straight line at one point, we might have a horizontal, we might have a diagonal, all just depending on the m and t. Now, why is this necessary? Let's go to the complex models and we'll understand. So in complex models, y, which is the output, is a factor or a function of x and theta, where theta are length parameters. Okay, so for example, a simple example is predicting the price of a house. So we have, let's say, a logistic regression equation. Let's say we have y equals a1 b1 plus a2 b2 plus a3 b3, where y depends on a. Okay, where y depends on a. So, or let's say y equals a b1 plus b2 plus b3, all in brackets. Okay, if y is the price of the house and a is just maybe the location of the house. Now we have, let's see, we have b1, b2, b3, b1 being, let's say, the size of the house, b2 being the number of rooms, and b3 being the number of neighbors. Okay, all these factors will actually when tweaked, will actually produce a difference value for y, which is going to tell you like the difference in price of the houses. So if maybe you have, let's say, a house at cantonment and a house at maybe, let's say, Osu, a house at cantonment and house at Osu, there are certain factors that are going to tell you if maybe the house at cantonment is going to be expensive than the house at Osu. And one is just the location. And another one is what is around that place. If you look at cantonments, we know we have embassies and stuff over there. If you look at Osu, we know it's just a normal rural town. So these are some of the things that influence normal decisions for models. Okay, just like how humans think, and we also make decisions based on certain parameters that come in our minds. These are some of the things that also affect models. So some examples of the models are some linear regression models, logistic regression models. You have the CNN, where you have ResNets and co. You have the GPTs, GPT 3.0, GPT 4.0. So these are examples of AI models. So now let's see some key concepts. So the first key concept is data. So for every model, or for AI in particular, the first thing that comes to mind should be data. Sorry about that. And now, when it comes to data, data could be represented in the form of text, images, numbers, sound, or whatsoever. So it is data that is being fed into the model before um, the model is able to make a prediction. Then we have features and we have labels. So consider a class where you want to know if the students are overweight or underweight. So you pick everyone's weight. Okay, so the input data over there is the weight of the people. You pick their weight and you're like, this person is 60, this person is 70, this person is blah 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 blah. But then what you are actually aiming for, which is the output, is to determine whether someone is overweight or underweight. Maybe you had a certain standard at 70 kg. So you're going to determine if the person is overweight or underweight based on what input value you've given. So what feature value you've given. You can't give height and then be expecting an overweight or underweight. Then we move to the model, which I explained earlier, which is the function that the machine learns to map input to output. Then move to training. So training is the process of teaching the model using data. So it's sorry about that. It's the process of teaching the model using data. So just as you have a kid, okay, and you want to train your child, what you do is you teach your child this, or do this and do that, do this and do that. Now, whatsoever you tell that child to do is what the child will actually end up doing. So whatever you give into the model to do, you tell this model based on when you see this thing, act this way, act that way. So there are certain maybe parameters. So just as I said, let's say you have a house and the features are the size and the location of the house. That will determine the price. You tweak your model to say, um, let it have, let's say, an increased feature, let's say an increased width for the location. So you want to be in a better location. You don't mind about the size. So you increase the weight for your location. So to the extent that anytime you are teaching your model that, oh, if I give you this particular this, then that means you are going to predict that this house is going to be expensive because looking over here, you've taught the model that it should look at the location more, and that happens. So that moves to where you predict. So the model applies what it's learned, what you've taught it to a new unseen data. You've taught the model that this and this and this. You've given it initial data already, and it has been trained based on that data you've given it. And so what happens is the unseen data, when it sees the new data, it actually predicts based on what it has learned. Then now you evaluate the model. You see how the model is performing, whether the model actually did well in predicting what you asked it to do or it didn't. So you use metrics like accuracy. So you check the model to see if maybe if it is yes, if the thing is yes, did the model say it is yes? If it is no, did the model say no? Good. So these are some metrics that you use. So accuracy, precision, you have area under curve, you have F1 score, you have a whole lot of them. So these are some things that are used to evaluate your model. So now how do we go deep down into that? So you have data collection. So with data collection, you visit some websites or you go around for them yourself. You can go to Kaggle for some data set like images. You can visit online. There are so many database platforms which store so much data where you can visit them. So that's where you do your data collection, or you manually can just collect them by recording and doing howsoever you collect this data. Okay. Then the next step is to pre-process the data. So in pre-processing the data, we are going to see one if our data is clean, if our data is good enough, if our data is very okay. We will not want to find some things missing in our data. So what we do, we either delete them, or if we don't want to find some, if we don't see some missing things in our data, we could clear a whole row, or we could fix in new values in those places. We could actually apply new pre-processing techniques to this data, whether you want to augment or you want to do anything you want to do to that data. Okay. Then based on what we want to achieve, is it classification, is it prediction, is it this, we choose a model. Right, after choosing a model, so a model could, you could choose a linear regression model, you could choose a decision tree, you could choose a support vector machine, and then you train the model with a training data set. Okay, so you can have a data set, and let's say it's 100%, and you split that data set. You can say you are splitting 60% for training, you are giving 20% for validation, and you're using 20% for testing. Then you evaluate the model's performance. So after training, you validate the data. Okay, you validate, sorry, the model. Okay, using your validation data, you validate the model, and then you can go on to test or not. You can go on to test your model. I'm so sorry for that. You can go on to test your model to actually see the performance of your model on an unseen data. Okay, so you can measure the performance using accuracy, precision, recall, or loss. So over here you have a small diagram over here. So you have your data preparation, your model training, your model optimization. So you want to um, train certain parameters which are called hyperparameters. Okay, maybe the learning rate, your number of epochs, or the learning rate being how well the learning rates being um how your model learns, how fast your model learns, your epochs is how many times the model is going to learn. You want to do all these optimizations before you evaluate your model and say, okay, this model is good. And then after that, you can deploy. Then you have your training data. Then you have your training data and your labeling. Now, why are we stressing about or stressing on um training data? Why are we stressing on just that part of data? It's not necessarily even data alone, but then not necessarily training data alone, but then why are we stressing on getting like a better data? Why? So we know training data is crucial for developing AI models, and since it consists of input features and their corresponding output labels. Now, the quality and the quantity of training data directly impacts model performance. So you can't. It's a system of garbage in, garbage out. You can't send um, a dirty data and then expect that model to perform well on a clean data. It's not going to happen. So if you have, let's say, a CSV file containing certain values or certain a table, let's say a long table, okay, containing certain features, and in one particular feature there are so many missing values, and you didn't clean this data, you didn't remove null values or you didn't fill them. Now what happens is when you feed that to your model has learned, and now you try giving it maybe an unseen data, try giving it something to predict based on that feature. You want a label to predict something based on that particular feature that had the missing values. What's going to happen is you might not like the um, values that will be returned. Okay, the performance of that model is not going to actually be something nice to you, and so it is necessary to actually have like a good data set where the data is cleaned, the data is pre-processed very well, and then you make sure that in doing so the model doesn't overlearn, or the model doesn't um, perform too well or perform like poorly. And that also comes to the quantity of data. So when you give a small amount of data to the model, you'd be surprised to see your model giving you like 100% accuracy or something, giving high, and you're happy. But then when you give it an unseen data, what happens is it gives you like a poor accuracy performance, or a poor accuracy metric, sorry. And so the quality and quantity um, of training data actually impacts your model performance. So a reduction in your quantity can cause your model to perform poorly. Yes. And so now data labeling organizes the data, allowing algorithms to learn from the examples provided. And this particular is found mostly in supervised learning. So in supervised learning, we tend to label our data to tell the model, hey model, when you see an orange and you see this, no, this is an orange. Like when you see an orange, this is an orange. When you see a lemon, this is lemon. We will not put oranges and mix them with lemons and call them oranges. Then we put something else over here. What happens is we'll make the model perform poorly when it even sees another orange, because it might call that orange a lemon. And so data labeling organizes the data. It makes it make the model learn very well that, oh yes, this particular thing is an orange and this particular thing is a lemon. So what are the types of machine learning techniques we have? We have supervised learning, where the model learns from label data, as I explained earlier. So you have you have you have your data being labeled as orange and lemon again, just like that. And you have algorithms such as logistic regression, linear regression, decision trees, random forest. So these are the algorithms that use supervised learning. Okay, these are the algorithms that use supervised learning. You have to label your data before you use this um, algorithms. You have unsupervised learning, where it uncovers hidden patterns in unlabeled data. So, for example, you can mix boys and girls in a room, right? And after mixing them, you can choose not to label them. Okay. Now, this is unsupervised. You don't tell the model this is a boy, this is a girl. The model looks around and looks at certain features. Oh, okay. Do do this particular set of people have breasts? Do they have this? Do they have that? What's the size of their head? What's the size of their this? What's that? So it looks at certain features. Okay, when it looks at them and looks at, oh, maybe these people have um some particular group of feature, it clusters them, puts them in like groups. Okay, and then it's able to identify that for you. So that's we have over here like the k-means clustering. So that's a popular example of an unsupervised learning. So for example, where you have an example is a customer segmentation. So um let's see, people send reviews, okay, to MTN. Once again, people send reviews to MTN. They don't actually, let's say they just type in the comment section or something else. They don't actually have a group and say this part is for bad network, this part is for fraud, or this part is for this. But then you have a machine learning model which looks at some patterns. So if it looks at maybe the word fraud in this particular statement or in this particular thing, it groups all of them and says, okay, these are reports from customers that this is a fraud situation. This this is a group of reports from customers saying that they have bad network and this and blah blah blah. So that's how unsupervised learning works. Then you have reinforcement learning. So in reinforcement learning, the agent learns by interacting with its environment and receiving rewards or penalties to shape its actions. So it learns by trial and error. So for example, I still want to use a kid. Okay, so when you have a small boy or someone beside you, a little kid beside you. When a kid does something wrong, you punish the kid or something, right? And then he doesn't do it the next time. And so when he does, when he goes round and he sees something, that same thing which you stopped him from, he's not going to do it again. So this is just basically how the model learns, or we call that the agent. Okay, so for example, you have a robot. Let's go to the next line now. Explain that. So you have over here, you have supervised learning, which predicts based on what you taught it. So you taught it that this was a triangle, this was a square, and it's going to tell you based on the next input feature you give to it that, okay, yes, this is a square or this is a triangle. Then unsupervised learning, it looks at certain features. Okay, here you have your square, you have your triangles, and you have circles. So it looks at these three, and it's like the circles have round, they all look round. The squares have four sides, and the triangle has three sides. Then let me cluster them like that and put them in their various groups, and then that's how come you have the three classes over there. Now you have reinforcement learning, where the robot is supposed to, let's say, get to the thing in the maze over there. And so how does the robot learn? So the robot knows, when I pass through this place, I don't see maybe an obstacle. And so it goes there, and if it sees an obstacle, it comes back again, then uses a different route. It comes when it meets another one, it changes route again. So doing that, it's actually like more of a trial and error. So it's like exploring other things. It's just going. And then at the end of the day, the robot gets to find like a maximum or a better point of like movement to the particular item in the maze over there. And so that's just how reinforcement learning works. So it's through trial and error. So for example, you have AI bots learning how to play chess. So when these AI bots are playing the chess with you and you defeat this AI bot, what happens is it learns that and says, no, okay, when I see a player playing this particular move, I'm not supposed to move in this. I'm not supposed to take this move. I'm supposed to do this way. And then that's just how the reinforcement learning is. Now I'd like to move to an API, which kind of seems different from our model stuff. So an API is a set of protocols or endpoints and data formats that defines how software components communicates and exchange data between systems. So, for example, there's a simple definition over here. So it's like a waiter in a restaurant that takes your order and delivers it to a kitchen. You go to a restaurant and the cook is the one, or the cook or the chef is your model. Okay, the cook or the chef is your model, and the waiter comes and it comes to you to ask what you want. So you send the waiter that, oh, I want banku, I want rice, and the waiter goes to the kitchen to bring you food. Okay, so that is just how an API works. Now, when we look at ChatGPT like this, okay, ChatGPT, the model itself is somewhere in the server, working on the servers and working in the cloud somewhere. But then, what makes it possible for us to access this model is the API. So you have the ChatGPT web app over there, right? As for ChatGPT has its own web app, so it's just linked directly to the model. It doesn't necessarily need the API. But then for people who would create chatbots, right, what they would do is to actually want to use ChatGPT, okay, they will go for their API. So you have an open AI API, or you can use APIs from Hugging Face, and this APIs give you access to models. Okay, so you create your own chatbot, and then this chatbot will actually connect you. This API, so it will connect the chatbot to the model. So it connects just the whatever Python code you have over there to the model, and so whatever you enter is going to chat GPT's model, whether GPT-3 or GPT-4. But it's not going to the actual ChatGPT you are seeing on your screen every time you access. But it's going to the model itself and it brings it to you, the chatbot that you created. So now how do we integrate the AI models via API, which I already spoke about? So you actually get your AI model ready. Then you visit your API provider where it is you can use OpenAI or Hugging Face. And then they give you a key. So you have your API key. And then this API key is what you use in accessing this model. Okay, so the model is just there, and then you can now send data to this model through the API through an HTTP request. So they're saving something how it works. So you send a request to the API forwards your request to the AI model. The AI model processes and generates a result, and the API delivers the result back to you. So one might be confused and think, oh, so let's say some models have particular APIs. Okay, some models have particular APIs that they use, and you cannot use a different API for a different model. Some have universal APIs. Some have universal APIs where like you can use um, an API to access like a different model. Right now, that is in it's in work. That's in work. I actually found out to realize that there are APIs which are being developed to make you access multiple models, right? So examples of some AI models in engineering, since we are engineering students, what could be some of these models we'll be using? So for code generation, for those in C, and perhaps they might know more than I even know. So you have GitHub, you have Copilot, sorry, GitHub Copilot, and you have Code 5, you have Starcoder, you have Lovable.dev, you have Bold.eu. So this is for code generation. Then in computer vision, you can use OpenCV. You have YOLO, which is you only look once. You only look once, which is for object detection. So when you go to the industries, most of the automation systems, like the robots that are responsible for, let's say, segregating stuff or maybe removing defective stuff, sorry, from the normal stuff, they use the YOLO the YOLO modeling to the YOLO model, okay, in doing all that. You also have TensorFlow vision. And then when it comes to speech and audio, you have Whisper, which is able to convert your speech into text. It's an AI model. You have 11 labs. When it comes to CAD or design, you have Autodesk AI. So this SolidWorks also has seen it has like an AI system embedded with it. Then you have Simulink AI. Okay, so this is an AI system for modeling dynamic systems and simulations, such as let's say the musculoskeletal system. You have something over there like that. You also have Wolfram Alpha, which is also an AI system that solves engineering or math problems. You have Glass AI, which is for summarizing biomedical literature. You have molecular transformers. Okay, you have small based models for chemical property prediction. You have medical image segmentation like ResNet, UNet for MRI, CT scan analysis, where it's able to map out features like cancer lesions or um, other things like on that medical image which you want to identify. It's able to map them out. You have the all famous ChatGPT. You have Claude. You have a whole lot of them. You have Gemini also over there, and so these are models which make engineering work so easier. So when a seaman or anyone gives us an assignment or something, you can just go online and then, based on proper prompt engineering, we'll be able to um, work well and then do our assignments so easily without stressing much by looking into research papers or something. You just get your research paper, give it to ChatGPT, prompt it very well, and it picks out certain features for you, and then you are able to do your assignments very well. So in conclusion, AI will continue to drive innovation. It's actually going to help people come up with more stuff, going to help people improve on other things, and it's no more a futuristic idea, just like what we see in the sci-fi movies. Because very soon the things in the sci-fi movies will be happening. So it's actually working in today's tools and industries. We've been hearing stories of Microsoft and IBM laying um, some software engineers off, all because AI has come to replace them. And so in our current world, or in our current circle, what we will have to do is to actually know how to use AI, since AI is a tool, right? AI is a tool. And so we'll need AI to stay relevant and innovative. We'll need AI to help us do certain functions. And so we shouldn't limit ourselves to the traditional way of doing things. We should always try to integrate AI into everything we do. And yes, that is it. So thank you very much. So I would like to take some questions if there's any. Thank you.
Okay, so thank you so much, Kekeli. Please, if there are any questions, you can type it in the chat so that they'll be addressed as soon as possible. So if there are any questions on the YouTube live, please type them in the chat. Okay, so if there are no questions, thank you all so much for joining our live session today. Sorry, our live session on the AI workshop series, and we'll see you next week for week 2. Thank you so much.